Hello everyone and welcome back. So this time we're going to be going over curvilinear motion in general and rectangular components. We won't get to rectangular components today, but we'll get there soon. So after today, you'll be able to describe the motion of a particle traveling along a curved path, no longer just a straight path, but a curved path. And we relate kinematic quantities in terms of the rectangular components of the vectors. Okay. So we're going to probably hit on applications and the general curvilinear motion section today. And next time we'll probably get into the rectangular components. So applications. Well, in all honesty, most things move in curves. We have very few things that stay in a straight line and never go anywhere. Pretty much nothing does. Now if we're on very short distances, maybe a drag racer is going in a straight line. If you're falling, I guess you're kind of moving in a straight line. But everything else, you can have a curve at some point. Now, the path of this plane, we can tell exactly how far away it is by using radar. And we can then figure out its coordinates as a function of x, y, and z and time. But do you think we can take that and figure out what the velocity and acceleration of the plane is at any particular instance? We know where it is at every moment in time. Can we figure out what its velocity and acceleration are? Or this one right here, we have a roller coaster car and it's going down at a fixed helical path at a constant speed. Can we determine its position or acceleration at any instant? Because we know what the velocity is because it's a constant speed. Now, if you're designing this track, why do you think it might be important to be able to predict the acceleration of the car? Well, we're going to learn later is that v squared over r is equal to our centripetal acceleration. And, think about it. If there's only so much force that can hold it in place, and the force pushing it out is too great, well, then these people fall off and gone. You might also snap people's necks if there's too sharp of a turn. So let's keep people alive and make sure we understand our rectangular components. Okay, so first off, general curvilinear motion. I'll get everything up here first. We have some sort of path function s. Now this is just going all willy-nilly. It doesn't have to be along one particular direction. And because it's going in every single direction, the x, y, and z, we typically use vectors to describe the motion. We have some origin, this is usually the observer, which is why we have an O, either for origin or observer, and we look at where they are. And we have this position vector r. It's bold, it's a vector. If you want to, you can always draw it with a little hat so you know it's a vector. Now the position of the particle at any instant is designated by this vector and it changes with time. And also the magnitude and direction of that may vary with time. Now just as we saw previously, if we know where it is at one point, we know where it is at the second point, we can determine what the displacement is. Displacement is the straight line distance. This delta s right there, that is the curved distance, okay? Delta r is the shortest distance between 2 points. Delta s, that is the full distance between the 2 points. This will happen during a time interval t. Now hopefully this is all looking very familiar. Like, wait a second, delta r, delta t, isn't that velocity? And you would be correct. That would be the average velocity. However, if we want the instantaneous velocity, well, then we have to take the time derivative of the position. If you want to do this numerically, you just make your delta t smaller and smaller. You just make it approach 0. So once it's very, 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 very small, you more or less have the exact solution. There will be rounding errors, and eventually those add up to being quite considerable. But for a single point, it can be fairly good. Now, one other thing to think about is, where is this vector v pointing? Well, it is always tangent to the path of motion, because at any particular time you're going in the direction that you're going. Now it is turning, you can see that this is going to turn, and that's caused by the acceleration. The magnitude of v, so the length of this vector, is called the speed. Speed has no direction. And the arc length, as we approach delta t as 0, our delta s, our path length, actually becomes the same as our displacement. So we can also define the velocity by differentiating our paths. However, this is the speed here, which why it's not bold or red. It is not a vector. It won't give you the direction when you do this, it'll just give you the magnitude. Now acceleration, well, if we can figure out what the velocity is and figure out how it changes, or sorry, figure out what the position is and figure out how it changes with time, then obviously we can figure out how the velocity changes with time. And the velocity, change in velocity over change in time, is simply equal to our average acceleration. So in this case, the v and the v prime is just the second instant. So we have an original velocity v, and then that has changed when we get to v prime. And as a note, you can see that these two arrows could be the same length. However, if their direction has changed, we still have acceleration. So your speed may be constant, but that doesn't mean necessarily that your acceleration is constant. It's only when your velocity, your true velocity, both magnitude and direction, is constant that you have zero acceleration. Now, similarly to velocity, if we want the instantaneous acceleration, we have to take a derivative. And so we can take the time derivative of the velocity, or this will become the second derivative of the position, because velocity was equal to dr dt, and this is the vectors here. And therefore, acceleration is equal to dv dt, which is equal to d dt of dr dt. And that's where we get this d squared r dt squared. Now, a plot of the locus of points defined by the arrowhead of the velocity vector is called a hodograph. The acceleration vector is tangent to the hodograph, but not in general tangent to the path function. As you can see right here, this is pointing more or less towards the center. However, if we make a hodograph where the velocity is pointing every single time, it will be tangent to that. And the reason for that is because the acceleration is always what's turning the velocity. And since the velocity is always following, the tip of the velocity is always following this hodograph, acceleration is what's moving along that hodograph. It's the same reason that your velocity is always tangent to your regular path, because your velocity is what is turning you along your path and actually describing your path. Okay, so we're going to stop here, and then next time we'll actually jump into those rectangular components. Hope you enjoyed this, and I'll see you all next time. Have a wonderful day. Bye-bye.